So this video, I'm going to talk about the existence of algebraic closures and their uniqueness. So so existence and uniqueness of algebraic closures. If you don't want to worry about this, you don't have to. You can just use that algebraically closed fields exist, and I recommend skipping this video if you don't care. Okay, so all right, so I want to prove. So the theorem that I want to prove in this video is the following: is that for every field f, there exists an algebraic closure. Okay, so this is part one. And then part two is if f1 bar and f2 bar are algebraically closed fields, or algebraic, let's say, are algebraic closures, because we define the notion of an algebraic closure. This is like the minimal one. Are algebraic closures of a field f, then f1 bar is isomorphic to f2 bar as a ring or a field. Okay, so this is the existence and uniqueness of algebraically closed fields. And so let me just say, kind of a spoiler, is the main tool here is Zorn's lemma. Okay, and so this says Zorn's lemma. So so what does Zorn's lemma say? It says that if P is a partially ordered set where every chain is bounded, then P has a maximal element. Okay, so that's what this says. And so what is the post set that we're going to do? So what we do is we're going to look at fields over F. So this is and then we're going to look at them up to isomorphism. Okay, so this is, so here, so fields over F. So this is, so these are all, this is the collection of K, which is a field, where K contains F and it's algebraic and extension. Okay, and then this is technically a category, so it might not be a set, because you could just like make copies of fields arbitrarily till you go blue in the face and just make them a really big set. But we always just going to restrict to a set size worth of fields. And then okay, so then so this is going to be a post set. So this is a post set where we say that so we will define that f1 is less than f2 if and only if there exists some injection. So this is a definition. So we're defining this. If and only if there exists some j from f1 into f2. So this is an injection. So this is that one can be viewed as a subfield of the other. Okay, so this is our partially ordered set. Okay, and so then a chain, right? So then chains are these things where you take, well, you're going to have one, so you're going to have, so I is going to be a totally ordered set. Right? And so this means that it'll have some every two objects are going to be comparable, and then we're going to have a collection of fields fi for I and I, where with maps, with these j maps here, maybe I shouldn't have used j because I wanted to use this as an index. So, but let's say with maps, let's call them FAB, from FA to FB for A less than B. So A, B are two index objects. So this is what a chain is. So it's essentially a collection. I would write them as like F0 is contained in F1, is contained in F2, is contained in F3, and so on and so forth. But it's not necessarily the case that we know that they're countable, right? All right. And so this is what's called a directed system, actually. So this is a directed system. And I'm going to make another video on this because in order to do one of these big theorems later, I need to talk about some properties of these directed systems. But again, not so essential if you don't really want to get in the weeds your first time around. But I'm just doing it here for completeness. This is a directed system, and given anytime you have a directed system, you can form this thing that's called the co-limit or directed limit. So this gives you a co-limit or directed limit. Okay, so there's a new thing that I can construct. This thing here, right? So this object, so this is a new field. So this is a new field. This is a new field built from the other fields. So it's kind of an abstract thing that I built from the FI, from this directed system. These FIs, or let's call them FAs and FABs. So this varies over this A varies over one index, and this varies over two indices built from this directed system. And I guess technically speaking, what is the definition? So what you do is you take a disjoint union of all these fields, and then you mod out by an equivalence relation. And what you'll do is you say that one element in one field, let's say, okay, let's not use C. We'll say, I don't know what I want to use. So we'll say that alpha in one index is related to some other beta, let's say this in some other index, right? If and only if. So there exists some C which is bigger than A and C which is bigger than B, such that these two elements agree after we apply this map. BC is alpha B. Okay, so it's like if you go further enough along down, you're going to regard two elements as equivalent. And this is how you construct the definition of this. This is how you construct this direct limit. This is how this new field works. So you got to check that as a field. You got to, and then these directed systems have some nice properties, but I'm not going to do that in this video. I'm going to punt to another video to do that. Okay, that's why I'm saying we're going to get into. If you really, this is why I'm saying we're getting into the weeds in this thing. Okay, so so we have this directed system thing, and this thing, so the directed system shows that here that the chain is bounded. Or sorry, this direct limit. Sorry, not the directed system. The directed system is the chain, but the direct limit, right, shows that the chain is bounded, right? And so by Zorn's lemma, this partially ordered set P, which is defined to be the fields. Okay, so the fields over F. That's what that notation means. It's not like a division. It's not a division. I'm just saying over. The fields over. So this is not a quotient or anything. So it's just like a weird notation to say that these are the set of fields that contain it. So this thing, you can either take it up to isomorphism, or you can just restrict to a collection of fields that are a set, right? This thing has a maximal element. Okay, and so by definition, okay, so there's some maximal element. So that proves. Oh, time out. I got to add some new pages to this notebook. Okay, I added the pages. Okay, so what does that tell us? So that tells us that so there's some. Let me go back here. So what does that tell us? That tells us that so that there exists some maximal element, and let me go back here. So this thing here has a maximal element. And that, what does that mean? So that means that there's something that is, okay, so let me just say this. So this is the partially ordered set. So this shows there is some F bar such that that is maximal in this. In particular, because of the way we define the ordering, for every F1 over over F, so F1 over F algebraic, there is some inclusion, J1 from F1 to F bar, which is an injection, is an injective ring homomorphism. Okay? So all of this together, that proves the existence of an algebraic closure. Okay? So now we can move on to uniqueness. So that concludes the proof of this part here. So we've proved now that these algebraic closures exist. It remains to do this next part. Okay? All right, so let's do that. So let's do the uniqueness. All right, so suppose F1 bar and F2 bar are two algebraic closures. Okay, so by the definition of the ordering, and maximality, we'll have a morphism from one to the other. So there exists some J from F1 to F2 bar. Maybe I should also say something else about these J's, right? So the fact that now I'm going to use another fact that I should have said before, but that this map here, the map J, J, when you restrict it, so F is contained in here, right? And so this map J here, when you restrict it to F, so F is contained in this field, and it's contained in this field, and this J from F to F needs to be the identity. A is equal, so let's say J of alpha is equal to alpha for all alpha in F. Okay, so it acts like a constant. It only moves the things above that aren't in F originally around. Okay, so, I mean, yeah. Okay, so uniqueness. Okay, so now we have this map, and here, J restricted to F is the identity. All right. So let's prove that. Okay, so let's prove that they're isomorphic. Okay. So first of all, this map is injective. So first, by definition, so we need to show that it's injective and surjective, and we have that it's injective. So this map is injective for free, right? So by definition. So it remains to show it is surjective. All right, so how do we show that it's surjective? Okay, so suppose alpha is in F2 bar, and it's not in the image of this J that we constructed. All right, so we know, so let M alpha of X be the minimal polynomial, and this is in F. Be its minimal polynomial. All right. So we know that M alpha. Okay. So we know that M alpha of X looks like X minus alpha 1, X minus alpha 2, X minus alpha D, where D is the degree. For and then we could do this in either field, either an F1 bar or F2 bar, but let's say alpha 1, alpha 2, and let's start it with alpha D in F1 bar. Okay? All right. So we also know that M alpha of X is X minus alpha so times G of X, for this thing has degree D minus 1 over in F2 bar of X. Okay, so we have this other viewpoint. Okay, so but there's another way to factor this. So using the map J, so we have that M alpha of X is equal to X minus alpha, J of alpha 1, X minus J of alpha 2, X minus J of alpha D in F2 bar of X. Okay, so there's this other factorization. So since, okay, so now we use unique factorization, right? Since X minus alpha, so this thing divides this, as an element of F2 of X, and F2, this thing here is a UFD because it's a Euclidean domain, so it's a PID, so it's a UFD, right? We must have that this X minus alpha must be one of the factors, right? So this is irreducible, right? So we must have, right, x minus alpha is equal to x minus j of alpha, I don't know what we want to call this, index a, for some a in this range. Okay, and so this proves this proves that alpha was actually in the image, which is a contradiction. Alpha is in the image of J, which is a contradiction. So what is it contradicting? Right. So it's contradicting that this assumption here that that it wasn't in the image, right? And so we ended up showing that alpha is in the image because here, you cancel the x's, and we showed that it has to be one of these things here. Okay, so that showed us that there exists an algebraic closure and it's unique. Okay, that's one of the main things that we have. We'll need just a little bit more about algebraic closures to prove the so-called fundamental theorem of Galois theory, and I'm going to do that in another video. Again, when the time comes to use it, I'm just going to state it and then refer to another video if I end up making that video. Okay, that's the end of this video.